Okay, section 1.6 deals with balancing chemical equations. I'll illustrate the technique by working through one of the exercises at the end of the section. So we'll look at the first exercise here, which is the burning of methane. So CH4 methane plus dioxygen, when they're burned, it produces carbon dioxide and water. To balance a chemical equation, we have to figure out the number of moles of each of the corresponding molecules here on both sides of the reaction. So let me flip over to my whiteboard. There we go. So this is section 1.6. on chemical reactions. And you probably remember doing these problems back in freshman chemistry. I doubt that you took a linear algebra approach. I'll show you the linear algebra approach here. So we're asked to balance this particular chemical reaction, CH4 or methane plus dioxygen producing carbon dioxide and water, H2O. Okay. And to balance the equation, we need to find actually the values of, I'm going to use A, B, C, and D here. So A moles of methane plus B moles of dioxygen produces C moles of carbon dioxide, and D moles of H2O. Okay. To come up with the corresponding linear system of equations, I'm going to look at the equations for the number of atoms of each of the particular elements on both sides of the reaction. So looking at carbon first, I've got one carbon atom here, or 1A carbon atoms. No carbon atoms here. On the right-hand side, the only molecule that has carbon in it is the carbon dioxide. And again, there's just one atom in that molecule. So A is equal to C. Taking a look at the next element, hydrogen. Okay, and the methane molecule, I've got 4 atoms of hydrogen in each methane molecule. And on the right-hand side, there's 2 atoms of hydrogen in each water molecule. The only other element is oxygen here. I've got 2 atoms of oxygen in dioxygen. And then here I've got 2 atoms of oxygen in carbon dioxide and 1 atom of oxygen in each water molecule. So here's my corresponding linear set of linear equations. I should note here, I'm going to illustrate the, where'd this come from? That's not, what was that? From hydrogen, 4A, and it should have been 2D there as the unknown parameter. So I should note it's relatively easy to solve this set of equations by hand. If we let D be our unknown parameter, I can solve this equation for A. Once I know A, I can solve for C from the top equation, and then knowing C and D, I can solve from B from the bottom equation. So solve this pretty quickly, without resorting to a linear systems approach, but I want to illustrate the linear systems approach. So transforming these into standard form, I've got A minus C is equal to 0, and then I've got 4A minus 2D is equal to 0 from the second equation, and then what I have here, 2B minus 2C minus D is equal to 0. Notice here in chemical reaction equations lead to a homogeneous system. All the constants on the right hand side are equal to 0. The corresponding augmented matrix is 1, 0, minus 1, 0, and then I'll have 0, 0, 0 here, and then I've got 4, 0, 0, minus 2, and 0, 2, minus 2, minus 1 for my augmented matrix. I'm gonna skip the steps here of reducing this to reduced row echelon form. It's pretty simple. It actually only takes a couple steps, but you know, so I encourage you to go through those steps. But the result is 1, 0, 0, 0, 1, 0, 0, 0, 1, minus 1/2, minus 1, minus 1/2. So here we've got 3 equations and 4 unknowns. The system is of rank 3. Remember the number of leading ones in the reduced row echelon form. So I've got one free parameter. You know, the number of unknowns minus the rank is the number of free parameters. Free parameter here, we can also see that readily from the reduced row echelon form. It is going to be D. So I'm going to let D equal to S and then solve for A. A is going to be 1/2 S from this first row. B is going to be equal to S. Remember, this corresponds to B minus D is equal to 0. So that's B is equal to D, or B is equal to S. And then finally, I get C is equal to 1/2 S. So, you know, writing it out in solution vector form, A, B, C, D is equal to S times A is 1/2, B is 1S, C is 1/2, and then D is 1. Okay. Now to balance the chemical equation, I want the smallest integer values of these coefficients. And I'll see that I can get the smallest possible set of integers by letting S equal to 2. I'll get 1, 2, 1, 2 here, with S equal to 2. Okay. And then so the final balance, so A equal to 1, B equal to 2, C equal to 1, D equal to 2. So plugging these values back into my chemical reaction equation. A is 1, so 1 mole of methane plus 2 moles of dioxygen will produce 1 mole of carbon dioxide plus 2 moles of water. And you can check here, I've got 1 carbon atom on both sides, 4 hydrogen atoms here, 4 hydrogen atoms here, 4 oxygen atoms here, 2 oxygen atoms there, and 2 more there, so 4 oxygen atoms on both sides. So this is how you can balance chemical equations using our linear algebra approach. Again, I could have solved, this is a simple enough system that I could have solved it by hand pretty easily. For more complex reactions, you might have to resort to you know, this linear algebra approach. Of course, for anything much more complex involving more unknowns than this, I'm probably going to turn to octave and reduce the augmented matrix to reduce row echelon form using octave instead of working through this by hand. Okay, I think that's the last example I'm going to work to today. This completes today's video lectures.